Hello, I'm Mike Douglas, and this is the New Technologies in Mathematics seminar of the Harvard CMSA. And today we're delighted to have Ben Edelman from the Harvard Department of Computer Science, who will tell us how to demystify transformers and attention. And so the talk will be about an hour. There'll be time for questions at the end. And as I always do, I offer to watch the chat. So if you have a question that you're not sure, it's perhaps very simple, or perhaps could be saved for an appropriate moment. If you put the question in the chat, I'll raise it at the appropriate moment. So with that, let's begin. Ben.
Yeah, great. Thank you, Mike, for inviting me to talk at this seminar. I'm excited to share our recent beginnings of some insight into why transformers and attention work so well. So I'm Ben Edelman. I'm a fourth-year PhD student in computer science at Harvard, and I'm going to be presenting on some joint work that I did recently with Serbi Gul and Cyril Zhang, who are both at Microsoft Research New York, and Sham Kakade, who has just joined Harvard as the new faculty in computer science. I'm going to be talking about transformers, and I expect that there'll be a diversity of backgrounds among the audience of how much you know about transformers already. But just to set the scene, there was several years ago a sort of revolution in the world of natural language processing, where previously the dominant architecture, neural network architecture used there was for recurrent neural networks and various types of recurrent neural networks. But then suddenly this new architecture, the transformer, took over NLP and outperformed previous methods by wide margins in many cases. But what's even more remarkable is that since then, transformers have been taking over basically all of deep learning and application domains of machine learning. So in computer vision now, many of the state-of-the-art models are no longer convolutional neural networks, they are transformers. AlphaFold uses attention mechanisms, which is the main component of transformers, for protein structure prediction. State-of-the-art reinforcement learning techniques use attention and transformers, as does automated programming, new methods for symbolic mathematics and theorem proving, as I know some people in this audience are interested in, and much else. And this new state of the field is rather different from what was just several years ago, where it was more fractured. Different architectures would be used depending on which setting you're in. Whereas now, almost any setting, you can take your data and plug it into a transformer. And so this really begs the question, why? What is it about transformers that makes them so good? What is it about real life problems that make them so amenable to be solved by the same architecture? And that's kind of the overarching question that I am interested in this line of work. And just by the way, I'm happy to be interrupted with questions during this talk. Cool. So just to explain how transformers were developed in the first place, they came out of natural language processing, where the kind of classic problem was the problem of handling long-range dependencies in input data. So on the left, I have this example completion problem. You see the beginning of a sentence, I know you are, but what am blank? Hello? Okay, I'll assume that's a mistake. I know you are, but what I'm blank, and you can easily figure out, just knowing statistics of what sequences of 3 words in a row are most common in English, you would know that it's almost certainly going to be the word I to complete that sentence. And this can be solved with very simple models, such as the N-gram model that was developed in the 1950s. But the real challenge of natural language processing is handling longer term dependencies in data, where you need to incorporate information from disparate parts of the text in order to solve your task. So this hard example, pretend this is like the end of a mystery novel. The detective says, there's only one among us who could have committed the crime, blank. This is much harder, probably too hard to be solved by transformers, if it's a good mystery novel at least. So over the decades, increasingly powerful approaches were developed to solve this problem of handling long-range dependencies. So we started off by seeing recurrent neural networks, which would take in the data one token or word at a time and incorporate that into a hidden state and produce a result. Later on, long-term, short-term memory networks were developed to explicitly try to retain information from long ago in the context to better solve this long-range dependency problem. And they were even better at solving NLP tasks. But still, LSTMs were not great at handling long-range dependencies. So a new class of mechanisms was developed called attention mechanisms to be used as an add-on to LSTM networks in order to make them better at incorporating information from far apart parts of an input. So this example is kind of a schematic for a translation from English to French. And the idea would be when you're translating a given word, you're doing a given output in French, you may want to pay attention to some sparse subset of the words in the input. And maybe figure out contextually which words in the input you want to pay attention to. And this is a very different paradigm from just having your model be completely sequential. So then some interesting things happen. After recurrent neural networks and also convolutional neural networks started being augmented with these sort of attention mechanisms around 2014 or so. In 2017, there was a breakthrough in which a group of authors at Google devised a neural network architecture that was not recurrent at all. It was basically just a stack of self-attention layers. I will explain what self-attention is. And this is the transformer. And since then, transformers have taken over natural language processing and the rest of ML, as I said. So before I explain the details of what these are, just like to get our typologies straight, attention mechanism is a kind of family of components that could be incorporated into a neural network that, loosely speaking, allow the network to pay attention to different parts of an input or an earlier layer selectively. Self-attention is a type of attention mechanism, which is the one I'm going to be describing, and it is the component of transformers. And transformers are just a neural network architecture consisting of a stack of self-attention layers. Cool. Yeah, so here's the thing. While transformers have been taking over, there is very, very limited understanding of why they are so powerful. This is a theme in the development of deep learning in general, where the science of why deep learning works and how it works is consistently lagging behind its applications in practice. And it's especially acute in the case of transformers. But I would argue that it's very important for us to start really studying transformers in earnest now, because they seem to be displacing other architectures and have better properties, more generality than previous architectures. So there's a chance that because they work in such generality, our understanding of why they work could be, in some senses, more general than our understanding of how previous architectures work. Cool, so here's the plan for the talk. I'm going to start off by giving you just an introduction to what makes up self-attention and what makes up a transformer. Then I'll talk about some intuitions people have about self-attention, like what properties it has intuitively that led to its design. And then finally, I'm going to talk about our recent work, which makes these intuitions rigorous and provides generalization and representational guarantees for transformers. Okay, so now I'm just going to get started explaining exactly what a self-attention layer is. So suppose we have this sequence as an input. So transformers are generally used for handling sequential data, which pretty much any data can be converted to. So here we have a sentence: the 5 boxing wizards jump quickly. And we're going to start off with this input, and we're going to end up at the top of the self-attention block with an output that is the same length. Now note that each of these inputs, each of these words is converted first into a vector that might be, it's a word embedding that might be of a few hundred dimensions in RD. Okay, so each of these outputs is going to correspond to the given input at the bottom. So let's focus for now on the output corresponding to the third input token. What it's going to be, the output is going to be just a weighted sum of some function phi of all of the inputs. So the alpha i's are going to be weights that sum up to 1. And I'll explain how they're generated. And in fact, phi of x in practice in the standard transformer architecture is just a linear transformation applied to the given input. So on net, this is really just a linear transformation of the input. And we can think of these weights as how much this output is paying attention to each of the inputs. So here we can see it's mostly paying attention to input 4. Okay, and when I'm writing down some of this notation, I'll put in red the parameters that are optimized by gradient descent or whatever iterative optimization method you're being used. So in particular here, this WV matrix is 3 parameters that can be optimized. Cool. So okay, now I'm going to explain how we obtain these attention rates. How does this output know how much to pay attention to each of the inputs? Well, here's how it happens. So we compute this sort of alignment score between each pair of inputs. So this one over here is the alignment between x1 and x3. It's how much x3 wants to pay attention to x1. This second one is how much x3 kind of wants to pay attention to x2, and so on. And in practice, the most popular method for doing this is this functional form, where basically each of the input vectors is hit with a linear transformation. So there's a transformation that turns, let's look at x2, x3 over here. So we're going to turn x3 into WQX3. This turns it into a query vector. And we're going to use another linear transformation, WK, to turn x2 into WKX2, which is our key vector. And then we just take the inner product. This is almost like taking the similarity between the inner product between the two vectors, but we first apply some linear transformations. Yeah, I mean, I'm explaining most of the details of a transformer. I'm leaving almost nothing out. And I think I'd like someone in the audience to be able to start doing research on transformers, maybe read up some other expositions after this and figure out for yourself what you think are the most important aspects of the architecture, because there are many different components here and it's unclear how necessary all of them are or how much each of them can be changed. Cool. So then what happens after we have the similarity scores is we push them through the Softmax bottleneck. So these scores are going to be real scalars, but they're not necessarily going to be non-negative, and they're not going to add up to 1. So what we do here is we exponentiate each of them and normalize to get the output. So alpha 3 here is it's just the normalized exponentiation of this third score function. Alpha 2, same thing for the second alignment score, and so on. And we could think of softmax as normalizing, but also as being a soft maximum. So it's pushing the attention weights towards being more sparse. And this is very crucial for understanding how self-attention works. Is this emphasis, this bias towards sparsity, which is what we're going to be exploring. Cool. So then, yeah, if we consider a different output, well, then you're going to have different alignment scores, and this will lead to different weights. So I've kind of abused notation by not having these weights be indexed by the output as well. They're actually, if the length of the input is t, there will be t squared total attention weights. And so generally computing the outputs of a single self-attention block takes quadratic time, and that is a big computational bottleneck in practice. Cool. And if we change the inputs, then the attention weights will change as well, of course. Okay, but the question is, okay, I didn't actually explain to you how we got these input vectors from the inputs words or tokens. So here's how we do it. Well, we really just have one big table that that lists for each word for example, each word in the English dictionary, it lists a vector that word is converted to. And this table or matrix is itself optimized through gradient descent and initialized perhaps randomly. Now this isn't quite enough to get us our input vectors, because as is, this architecture is kind of in some ways invariant to permutations of the input. It can't figure out, it doesn't care, like in terms of these weights, in terms of the final output, which order the words and the surrounding context appear in. So we have to give it some way to care about order. And the way we do that is by adding what are called positional embeddings or positional encodings. Now, in this case, we have 6 inputs. So that means we really just have 6 vectors, P1 through P6, that are the same dimension as the word embeddings. And those are fixed as you change the words. And those are also typically trained during the course of learning, although they can also be set to a fixed initialization if you do that smartly. Great. So yeah, if you change the words, then the attention weights will change, but note that the positional embeddings are staying the same. Okay, so that is this is basically a full description of a self-attention head. In here is everything you need to know to understand the mechanistically how a self-attention head works. But you'll notice that there are various design choices that went into this. There's the choice of what functions to use here. We use Softmax. There's the choice of what are we using as phi, what are we using as our score function. And part of what we were interested in is why do these choices work well? What can we say theoretically about them? I'm just going to pause for a little bit, see if anyone has questions about the architecture.
Hey, Ben, how do you get the position embedding in the first place?
Yeah, great question. So maybe the most common way of doing that is you start by randomly initializing it. So you just, in this case, we just have 6 vectors, P1 through P6, that are just initially maybe randomly chosen according to some Gaussian. And that's how they are at the beginning. And then from then on, during the course of training, you have some objective, and the gradient can propagate all the way through, all the way down to the choice of those vectors. And then each of the P1 through P6 will be optimized through training. I think it's a very positional embeddings are somewhat mysterious, and I think they're poorly understood. In particular, it seems like they in practice might allow for an output to figure out like, hey, what's going on, like, let's say several positions away, they might be able to use these positional embeddings to compute distances, for example. And it's no one like, I haven't seen proof that that will necessarily happen if you train on any given distribution.
And sorry, one related question. So is the gradient flowing all the way through the word embedding too, or are you fixing the word embedding to begin with?
Yeah, great question. Yeah, typically the gradient is flowing all the way through the word embedding as well. Yeah, so that's I guess why I put it in red over here at least, but I guess that wasn't so clear. And in fact, like one way to think about this is previous to transformers and these sort of contextual word embedding methods, it was very popular to come up with a fixed word embedding for each word using a neural network like word2vec. And then let's say you have the word jump, and that would have one vector no matter where it is, like doesn't depend on its surrounding context. Whereas what transformers allow you to do, or what this strategy of training word embeddings allows you to do, is have the embedding depend on the context. So if a word has multiple meanings, it will disambiguate between those multiple meanings. Cool. Okay, so now I'm just kind of summarizing this as this is all one attention head, and the parameters of the attention head are these three matrices: WQ, which gives us those query vectors; WK, which gives us the key vectors; WV, which gives us the value vectors. And yes, also the positional embeddings and the word embeddings are trainable, but that will only happen at the very beginning of the network in the first layer. Now, okay, another important thing to note is that each of these matrices has dimension that does not grow as the length of the input sequence grows. It's their fixed dimension, it's same dimension. They'll be only growing with the size of each of the embedding vectors. So that's an important thing to note when we're talking about generalization. Cool. Okay, so now let's talk about what a transformer is. So I said it was an architecture that is composed of self-attention heads. Okay, now so this whole thing is an attention head. I guess I'm representing it by this pentagon. We could have, starting from an input, we can send it as input to multiple different attention heads, and this will form just one self-attention layer of a transformer. So each of these will have its own different trainable matrices. And in practice, you might use several dozen heads in a given layer. Okay, so the input's provided to all three. Then the output from these attention heads is combined back again. You just add up these vectors together along with the initial vector and normalize. And so we get our combined output. And then the last step of making a full transformer layer is to add these fully connected networks on top of each of these output vectors. So these are each have identical weights that are taught, there's weight tying that's going on. So these are each trainable, but they're identical. And notice again that the number of parameters, the number of distinct parameters here also isn't growing with the length of the input sequence. Okay, so this whole thing is a transformer. So at the end, all we have to do is one more adding and normalizing. So these arrows that are going all the way around are residual connections, which is a popular component of various deep learning architectures, which allows for inputs to be, tries to make it so that inputs are kind of preserved in future outputs. Okay, and this is one transformer layer. So if you just take this setup and you stack it again and again, you have a transformer. So that is a complete description pretty much of how a transformer works. Now, I guess first any questions about the transformer architecture? And there are variations of this architecture, of course. This is originally a transformer actually had two separate parts, the encoder and a decoder, which are a little different, but now just the straightforward, maybe it can be called a decoder only stack, is most popular.
So just another quick question. So on those add and normalize layer, does it make sense to have like attention of those attention heads? And instead of just adding and normalizing them, could you potentially train another attention layers from those?
I don't think I quite understand what you mean by that.
So you have multiple attention heads, and when you combine them, each of the output, could you do an attention on top of those each attention heads?
So you mean like another layer of attention on top?
Yeah.
Well, I mean, so just two layers of attention. I mean, in the end, we do end up having another layer.
Oh, I see.
Heads on top here. So it is stacks of attention. They're just not there. We have these fully connected networks in between, which are able to represent a more rich set of functions. Yeah.
Oh, what you're saying, Peter, would be something more as opposed to operating on the token level, operating on the whole output of each of the heads and using those similarities.
Yeah.
Does it make sense mathematically? Whether people use it. Yeah.
I guess we can try.
Right.
Right. Yes. I mean, as opposed in the end, yeah, we might have many attention heads in a given layer, but then they all are combined back together before the next layer happens. So, I mean, this seems to be effective, but maybe there are ways of playing around with it and getting something better. I don't know. Cool. And I'd just like to provide a single example of how you might actually train this transformer, like what sort of how you might apply it to a given task. So this example is the masking task that is used for training the popular network BERT. So in this case, you would take your inputs passage, mask out some of the words that you want it to guess. So particularly, we're literally just going to replace those words with a special token called mask that is going to map to a particular embedding. And then you just run this through a transformer and look at maybe what is the embedding of that vector up here. And then we would convert that vector back into a word by looking at that matrix of word embeddings and seeing which word vectors it's most similar to. So you'd end up actually with a distribution over words. But there are various other strategies for training transformers that are used in practice. This is just one example. Great. Okay, so that's how a transformer works, but the big question is, why does it work? Why does this particular architecture work so well on so many different domains? It's, if you're hearing the description for the first time, you might think wow, this seems like it has a lot of arbitrary decisions that went into it, and people had intuition that led to each of these decisions, but it often wasn't very rigorous intuition. So the question is, can we make this rigorous? So here's one intuition that is also observed in practice, which is that maybe it's important that these attention weights are sparse, or very mixed alternatively. So I guess this is a diagram from a particular paper that was looking at some attention heads from the BERT model, and I don't think it's important to really understand this too well because it's a somewhat complicated diagram, but the idea is In these pictures, the right-hand side is the output tokens and the left hand is the inputs. And the lines are telling us how much attention each output is paying to each input. And these are each for just a given one head in a given layer. So this is, for example, the 10th head in the 8th layer. And you can see that, okay, these are mostly pretty sparse. Some of them, some of the tokens have weights going to all of them, so they're very uniform. And in particular, these authors were able to interpret the weights as relating to specific grammatical relations. And there's been a whole recent outcrop of papers that opens up BERT and tries to interpret it in terms of seeing whether it's actually doing things that a classical natural language processing pipeline would do. There's intuition that maybe, okay, if there's a bias towards learning sparse patterns in each layer, in each head, that this is a good inductive bias for transformers to have. Another example, this is from a paper on applying transformers to reinforcement learning. So in this in this paper and another one that came out at the same time, they had this very clever idea, which is to just make the input sequence the sequence of states and actions and rewards of an agent in a reinforcement learning environment. And you just give it the task of predicting what its future states and actions and rewards are going to be. And then if you want it to make good, if you want to figure out what's a good set of actions to take, you can just say, okay, if I condition on my rewards in the future being very good, what is my prediction for what my actions were? And then you can come up with decent actions. So anyway, this is another visualization of the attention weights in two different heads of the transformer they used. So in this case, on the one axis, they have the outputs, and the other axis, they have the inputs. Each input and output corresponds to a state or action at a different step of time. And again, there's a strong bias towards sparsity, it seems, in some interesting ways. In particular, this one seems to be learning some long-range dependencies. And at a conceptual level, if there is such a strong bias towards sparsity, then this would give us some explanation for why transformers are good at handling long-range dependencies. Because being able to learn any function is just too broad. But if you're able to learn maybe sparse long-range functions in a given layer, then that might be specific enough that you won't overfit. That's the rough intuition here. Right, and as I mentioned before, Softmax, the use of Softmax is key towards leading to this bias towards sparsity. Yep, so here are the questions we concretely studied in our new paper. So the overarching question is, what is the inductive bias of transformers? And in particular, we looked at generalization, representation, and optimization. So generalization, specifically, we're looking at what can we prove that transformers won't overfit, and we're restricted, conditional on the norms of the matrices, the trainable matrices being bounded. Why do we care about that? Well, our goal is to show that these bounded norm matrices are sufficient for transformers to be able to approximate a rich class of functions, in particular sparse functions. And then finally, ideally we'd have a good understanding of optimization. Do these transformers actually learn these functions in practice when you train it on them? Even better would be to have a theoretical understanding of optimization, but that's very hard, and we as yet don't have such an understanding. All right, so combining all these three together, showing that sparse functions can be represented in each layer with generalization, and that these are optimized in practice is a phenomenon that we call sparse variable creation. The idea being that each layer is kind of creating these sparse variables from the previous layer that can then be used as inputs to the next layer. Okay. And motivating guiding our practice of theory was the goal of having a theory that's resilient to architectural advances and changes. So if you look at our paper, our results are stated in general terms. They apply to various choices of this phi function, score function, an alternative to Softmax, and turn out to specialize very well to the versions of these that are used in practice. But our hope is that our theory could still apply to the architecture that's used in 2025, let alone 2030. Great, so now I'm going to talk a little bit about generalization bands, but first I'll pause to see if there are any questions. Okay, so this is going to be just a very elementary explanation of how we should get a generalization bound in learning theory. So, because I imagine that some of the audience hasn't studied learning theory before. So, we're going to assume that when you train your network on a given problem, that you'll always find a function, or you always land on parameter matrices that lie in some finite class H. So suppose that were true, then this implies a generalization bound, a upper bound on the gap between the training error and your test error on the whole distribution with high probability. This is the guarantee of pack learning. And the way this is the basic way this is proved is just using a combination of concentration inequalities and union bound. Basically, this is a uniform conversion. So we consider the worst case generalization gap across all functions in the class. And we know that for any individual such function, the training error is a finite sample estimate of the distributional error. And so we can use a concentration bound to bound that, and then you just multiply it by the number of such functions with the union bound. Rearranging this expression is what leads to this expression. Okay. So any questions so far?
M is the number of samples, or?
Yes, so that's true. I didn't explain what all these terms were. M is the number of samples in your training set. D is the distribution of input the distribution of x's and y's. S is your training set. Right, and here I've just, for this expression, I've just set epsilon to be a constant, a small constant, and so you can ignore it. Okay, so this is just like the foundation of learning theory, basically. But okay, when we want to apply generalization bounds to neural networks or almost any modern mesh method, you face the problem that the class of functions that is representable by a neural network is continuous, not discrete. And so the size of H is actually infinity, and this is useless. So instead, you'd use continuous notions of size or capacity of your hypothesis class that have been developed over the decades, such as DC dimension or covering number, in order to provide similar guarantees in this continuous context. Now, one thing I'd like to highlight is that informally, people often like to use just count the number of parameters in your network in order to say that, oh, it's going to, the classical theory would say it would overfit or not overfit. But just as an aside, like the parameter count does not formally imply this sort of bound. And in fact, in the example of transformers, the number of parameters does not depend upon the input length t, and yet we can prove lower bounds for these quantities that show that, in fact, the capacity does need to grow with t. So it's not so trivial to understand. In particular, in our paper, we use covering number. We use in particular infinity covering number. So the intuition behind covering number is that sure, there may be infinitely many possible functions that we could learn, but a lot of them are very close to each other. And if if we can find a small enough, finitely large covering of functions such that every function is close to one, maybe that would allow us to also say that every function has a generalization gap that is governed by the generalization gap of functions in the cover. Okay. So yes, these infinity norm covering numbers is what we use. So you consider a given data set, you ask, what is the smallest subset of the class of all functions, such that, what's the size of that subset, such that for all functions, there's an element of our cover that is close, that gives close outputs in an infinity norm sense. Infinity norms are actually less popular than, let's say, L2 norm covering numbers, but we found that they would work better for transformers. Cool. So here is a statement of our main generalization result, informally at least. So the result is, with probability, with high probability, this is an arbitrary constant, the error on the training set minus the error on distribution is going to be bounded by this quantity, which depends on some C, which is a quantity that is a function of the norms of the matrices of those WQ, WK, and WB. It's also governed by D, which is the dimension of each of those word embeddings. And finally, it's going to grow logarithmically in T, which is the number. Hold on, no, this slide is incorrect. The sequence length is T. M is the number of training samples. Sorry for that. So T is the length of the input sequence. Yeah, so remember I said that we can prove that there needs to be some dependence on T. Proving that it was only logarithmic is, I think, perhaps like one of our most important results here. Okay, so that's key. Any questions about this bound? The statement of it?
And I have a question. I mean, this is nice and intuitive. So does this answer why transformers are better than RNNs? I mean, is there anything here that's...
No, so I'd say just a generalization bound itself, this is kind of like, this is saying this is that transformers are sufficient in some sense. I mean, sorry, I would say that generalization is necessary for transformers to be competitive. But people also have generalization bounds out there for recurrent neural networks. It's really more the representation that I'm going to cover next that's going to explain what's special about self-attention.
This formula seems like a very strong dependence on the embedding dimension D. I mean, do you think that's really there, or that's just the nature of what you were able to prove?
I'm not sure. So if the norms were unbounded, so if we didn't have bounds on norms, then this D is necessary to be. So what I'm unsure about is whether this, I think this might be able to be improved. You might be able to eliminate, I suspect the D is necessary, but we might be able to improve the dependence on the norm bounds. But I don't have, depending on what norms you're using.
And of course, empirically, you need a certain D. The error goes way down. For
yes, right. So empirically, it doesn't hurt you to have larger T's. So maybe that's something wrong. And in fact, one thing I don't have explicitly in my slides is we apply this to come up with a generalization bound for a full transformer that consists of many layers. And our generalization bound gets worse with depth, when in reality, generalization doesn't get worse with depth. And this is a common pitfall of generalization bounds that are able to be found by state-of-the-art methods in deep learning.
Yeah.
Great. Okay. So just to discuss one little fact about the softmax that was crucial for our proof. If this were not true, then the generalization bound would not go through. You would not have that log T dependence. This is all I'm going to tell you about our proof because I don't have time. But it's important, it turns out, that if you take an input vector to softmax, and you just change it by some bounded amount in infinity norm. So you can change all of the components, but only by a certain amount. Then this will lead to only a bounded change in the one norm of the output. It shouldn't be obvious why this is important. This video is showing the output of softmax for when an input is wiggled a little bit in infinity norm. You can see it stays pretty close to the original in one norm. But just as some intuition, we're trying to get an infinity norm covering bound. And this inequality allowed us to start with some L1 Lipschitzness bound and turn it into an infinity Lipschitzness bound. And this was very helpful for getting the covering number result we wanted, which does have a somewhat involved proof. It was not just like doing the necessary inequalities, there was some creativity required. Great. Another useful property of softmax that we use for our next result is this exponential saturation, what we call it, which just means that it has a bias towards sparsity, basically. As we scale up one of the input components, the output vector of softmax will go very quickly grow towards just being an indicator vector. So here we're just scaling up this C, and you can see it goes very quickly towards the 1, 0 vector. Yeah, so what this allows us to do is prove our representational result, which is that a transformer layer can approximate arbitrary sparse Boolean functions of the input. And in order to do this, the norms of the matrices require scale only as a function of the sparsity. So in other words, this is saying that this is not saying anything about whether in practice, when you train a transformer, it will learn a sparse function. It's just saying that there exists a setting of weights that will lead to it approximating a given sparse Boolean function. Intuitively, this softmax is allowing for some sparse variable selection. So it kind of selects a small subset of the input variables. And then the fully connected network on top allows us to apply some arbitrary function to that sparse set of variables. So some examples you might consider are sparse conjunctions, disjunctions, or more complicated things like those grammatical sparse functions that were in the NLP example I discussed earlier. Okay, so this is our second main result, stated very informally, of course. Okay, so combining these two, the generalization plus the representation, you can compose these to a kind of interesting statement, which is that, in particular, the sample complexities statistically required for learning an arbitrary sparse function, if you have just one layer of a transformer, scales like some function of the number of relevant variables, the sparsity, times something that grows roughly logarithmically in the length of the input. Now, what's interesting about this is that this is exactly the statistically optimal form of the sample complexity for learning sparse functions. So somehow this architecture that was not developed explicitly to get some statistical guarantees for learning sparse functions, in fact, does have very strong statistical guarantees for learning sparse functions. And so intuitively, if each layer is learning sparse functions of the previous layers, you can build pretty rich representations this way. Okay.
Just to be sure, when you say sparse function, you mean one that depends on a bounded number of variables, or?
Yes, I didn't actually explicitly state it here. That is exactly right. It's a function, so that would depend on a constant number of the input variables. And one thing that we don't cover in this paper is that really the attention is even more powerful than that, because the variables that it pays attention to can be adaptive to the context. Like it can pay attention to a different sparse set of variables depending on what the input is. And this is kind of hard to formalize. And so we've only covered the simple case, really, where the variables are always the same. Okay, so here's an example plot. where we want to look at, okay, whether these functions are actually learned in practice. So here we're training a one-layer transformer on this problem, which is you draw your X, your input sequence, uniformly from a binary string, which then needs to be converted into the input vectors using some embedding, which I'm not going to describe. And the output is just the conjunction or product of three hidden variables, like three unknown variables. Okay. And so here what this plot is showing you is as we increase the length of the input, how much does the critical sample size grow? The critical sample size is the number of samples required such that the network doesn't overfit on that sample. Because in practice, the transformer will always basically reach zero training loss, even if the sample is very small. Only when the training set is big enough do you not overfit. And here what we see is, okay, this is a logarithmic. This is the x-axis is logarithmically scaled. This is roughly linear. So this is basically showing you a logarithmic in t scaling behavior. It's a logarithmic scaling law that matches intuitively what we'd expect from our generalization bound. So this is showing that at least in the case of conjunctions, that we see what we expected in practice.
So again, just to be clear, so the input for a given token is a two-valued choice of vector, which is the embedding of the 0 or the 1, plus a positional embedding, which started out being some random variable for each position, and then those embeddings.
Yes.
Okay.
Exactly. So there's a choice of embedding for 0 and an embedding for 1, and yes, and their positional embeddings.
Right, okay.
Exactly. Okay, so that's conjunctions, and again, this is pretty much the extent of pretty much done. Just one more thing I want to show you, which I find pretty interesting, which is when we look at a different sparse problem, which is the problem of parities. So now we're just adding some input bits mod 2 instead of multiplying them. Now, parity is a notoriously difficult problem from an optimization perspective for algorithms like gradient descent to solve. So in particular, if it's not a sparse parity, then it is literally impossible for a gradient method to learn parities. If it's sparse, it may take a very long time. What we found is that a single layer transformer will learn these sparse parities. In fact, it'll do it in the roughly the optimal scaling that you would need statistically. And it has this very interesting training curve, which is it starts off for most of training, just having trivial accuracy. So this is the loss that you would have if you were guessing randomly, or actually not random, I guess, just if you're just random guessing. And then at some point, suddenly, so in each of these training curves, this is many different runs, it suddenly jumps to having perfect accuracy. And this is a behavior we're trying to explore. We have a project exploring right now. And in general, I think understanding the path of gradient descent and optimization in transformers is an important direction for future work, and our theoretical understanding will be necessarily incomplete until we understand it. So I think I'm pretty much out of time, so I'm just going to wrap up by saying some problems I think that are exciting for the future, for future work on transformers that emerge from our work in particular. So one thing is that, okay, we introduced this idea of sparse variable creation, which is kind of a formalization of things that were already in the air, but we don't have a more than intuitive explanation of why sparse variable creation specifically leads to transformers being so capable. Like what we know that it should lead to good generalization, but what are the properties of networks with sparse variables that lead them to be so capable? Second thing is, again, I think it's interesting to understand optimization in transformers And there are many other questions like, as Mike brought up, improving our generalization bounds and our other quantitative results. So with that, thank you. Here's our paper. I'd like to really thank my co-authors once again, and thank you all for listening.
Thank you. Do we have questions from the audience? I have a question, which I thought the talk was very clear, but I'm now asking myself, what exactly did sparse variable creation mean? Did you give a formal definition, or could you say it again briefly?
Yeah, so okay, it is a little wishy-washy. Yeah, so I didn't really give a formal definition. That it's referring to sparse variable creation is kind of the fact that it's this formula right here. It's the sample complexity for learning sparse function skills like this.
Okay,
so they can be both represented and generalized. Yeah.
Sparse regression in an optimal way. Okay. Yeah. Okay.
Yeah. Exactly. So I think it's like pretty cool that somehow it matches the optimal algorithms that have been developed for specifically for this problem. Roughly, I mean, up to what this function is and what the polynomial is. And so.
Is there previous work on learning to solve complicated problems using sparse regression? I mean, I would think like, if not a holy grail, at least a real benchmark would be to show the extent to which a transformer could learn a formal language. And so, obviously you need to use, results like what you're describing as the input, but now have people ask, suppose I put together things that do sparse regression, can it learn a formal language? Was there literature like that in the past, do you know?
I haven't seen anything like that. I don't know whether it exists. I think it would be interesting to try to see what happens if you replace some of the attention components here with something that is explicitly doing sparse regression.
To ask the related question, do you know any good paper that addresses the problem I just asked? Can a transformer learn a formal language? Or what class?
Not off the top of my head, but I think you should look it up, because I would assume that such papers exist. Yeah,
I've seen a few, but not many.
Yeah. I don't know. I don't know one in particular that I can recommend strongly. And one other thing to note, by the way, is that we're not saying that they're only going to learn sparse functions.
Right.
In particular, it's also easy for them to represent nearly uniform mixtures over the inputs. So the actual inductive bias might include the sparse variable creation, but it probably is a little more complicated. That's something to do.
Yeah. Okay. Matt Farrell.
Yeah, hi, thanks. So it seems like if creating sparse variables is sort of a key thing, you can compare with having a sparse encoding of the words and their positions, and then just feeding that to some, I don't know, feed forward neural network, for instance. So maybe you can reiterate again, like what this sort of pairwise comparison structure, what kind of magic that adds to the picture beyond just having sort of a big sparse distributed memory that includes position.
Okay, let me make sure I understand. So what do you mean by sparse distributed memory in there?
So I guess I'm thinking of like you have a sparse encoding of the information, which is the words and their positions. So it's kind of like a big dictionary.
Sure.
And then you just kind of learn, I mean, you have this huge dictionary and you have a huge number of parameters that you can use to map those entries to desired outputs. So as long as you have enough parameters, you can do that. But, I suppose generalization might not be good, but there's this extra kind of magical thing that's happening where you're doing all these pairwise comparisons. But I don't fully understand how that pairwise comparison is really kind of like essential, basically. It's still a little murky to me.
Right. No, that's a good point. So the pairwise comparisons are crucial for picking out this, which variables to select for. And when we try to prove this representational result, it was crucial to have the pairwise comparisons. And that does allow you to pick out different sparse collections of variables for each output. So it can be very distinct across different, outputs. It's also probably important in making it so that the sparsity can be adaptive, which again is something that I don't have a great handle on, but it's something that wouldn't be, I guess, handled by the sort of more rigid architecture you're suggesting.
Yeah. Okay. So it helps with like the sparse combinations.
Yeah. So you can think of this, define the sparse variable selection as just basically acting on the positional embeddings. And then in our proof, then you act on the word embeddings and the MLPs over here.
Thanks for the additional intuition.
Yeah, well,
More questions,
I have a question.
please?
I think you're saying that sparsity is an important feature and a sufficient feature for attention. And I know there's like some ways to try to speed up attention by using a sparsity, like the reformer is one example of that. And I wonder if your research has any kind of like tie-ins, and maybe one thing is like the fact that you explicitly say, well, what if we bound these weights? Maybe that's a way to force your model to be sparse, and then when you replace it with some kind of sparse thing, then you're not losing anything by doing that. I was just curious if you had any thoughts.
Yeah, that's a good question. So there have been a lot of attempts recently to mainly aimed at improving this quadratic computational cost by sparsifying the matrices involved in the computations and directly sparsifying them. I would say that, so I think optimization is probably a lot of the story here, and we don't understand it, and that's probably having a big effect on how well these methods are working. For example, I discussed how there's this WQ and WK matrices that are parameters for the model, but in reality, those are just multiplied directly together. And so if you were just caring about representation and generalization, you can replace them with one matrix, but somehow it works better for optimization to have them be two matrices. So I'd say like a lot of aspects of why transformers perform well probably have to do with the actual paths found by SGD. Let's see. Another thing I'd say is that if again, I think it might be important to have the ability to mix, in addition to be able to represent sparse functions, to be able to represent nearly uniform mixtures over the inputs. And that's something that you might lose if you restrict your network to only having sparse. And I guess the final point is you talked about restricting restricting the norms of the matrices during training. And in fact, that's like roughly what happens when people do weight decay, which is very common in training transformers. They're not literally restricting the weights to with the same norm bounds that we use, but I think like restricted norm bounds are like a reasonable rough approximation to capture some of the inductive bias, that we see in real life.
Okay, thanks.
Yeah.
More questions? Okay, well, if not, let's thank Ben for the informative talk, exciting direction. And next week, we'll be having James Bonifacio speaking about constraints on the spectra of hyperbolic manifolds using the bootstrap. So I look forward to seeing many of you there, and thanks for joining us. Thanks again, Ben.
Thank you.